All right, so in this video, we're going to talk about surface area now. In the last video, we worked on parameterizations of surfaces, and so this would be, let's say, a parameterized surface with the two parameters u and v. So if that's what that is, and it is a smooth surface, and a true definition of smooth in this particular case would be where the partial of r with respect to u and the partial of r with respect to v are continuous. So assuming that's the case, then the surface area of that surface on some region is going to be given to us by this formula right here, where this is going to be the magnitude of the cross product of the partial of r with respect to u and the partial of r with respect to v. Now, we're going to use this formula, we'll use it in a variety of ways moving forward as well, but right now we're going to use this formula to come up with another one for where if the surface isn't parameterized, we can still come up with the surface area. So to do this, we'll say consider the surface z equals f of xy, which to start is not parameterized. If we are going to parameterize it then, we could do r of xy being xy and then f of xy, a similar parameterization to what we would have done for for curves back in Calc 2. So then if we use this formula right here, where I want to compute now the partial of r with respect to x, cross it with the partial of r with respect to y, I have my I, j, k on top, and then partial of r with respect to x would be 1, 0, and then f sub x. So 1, 0, f sub x. And then partial with respect to y would be 0, 1, f sub y. 0, 1, partial of f with respect to y. So when we run this determinant now, that's going to give us negative f sub x, negative f sub y, and a 1. Now for the magnitude of it, that's going to take us down now to the square root of this thing squared, so f sub x squared, this thing squared, f sub y squared, and then this thing squared. So that's going to give us f sub x squared, f sub y squared, and then plus 1 squared. So putting that all together, we can also now use as a formula for surface area the double integral over region R, the square root of 1 plus f sub x squared plus f sub y squared dA. So this formula, the original one, is a good one when you have a surface that's already parameterized or it's easy to parameterize. This one would be a good formula if you were just given z equals f of xy surface where you can just plug stuff in for those two things. All right, so for our first example, we're going to find the surface area on this surface between y equals -1 and y equals 1. Now, for this particular one, it is going to be easier to parameterize this and then move forward using that first formula. So that's where we'll go ahead and start. We're going to do r of something, and then given the x squared plus z squared equals 10, if this was a y squared and I asked you to parameterize it, you will have done that pretty easily because you've done it before. It's a z, which doesn't change anything other than the variable that it's going to replace. So for example, x is going to be that square root of 10 cosine theta, and then now the z is going to be the square root of 10 sine theta. And so remember, what I did there is I just used that Pythagorean identity from trig, knowing that this thing squared plus this thing squared is going to give us that 10. So nothing new there, which just, again, in a different place. It's no longer x and y, it's x and z. Now, the only other part we're missing is going to be y, but if you'll notice again, you've only used one parameter and you're allowed two, so we're just going to let y be itself. And so our parameterization would be with respect to y and theta. Now, we'll go ahead and put our bounds on here. We know that y is going to be bounded between -1 and 1 from the given information, And we also know that theta is going to be bounded between 0 and 2 pi, as it would be for a surface like this, given this parameterization. All right, so for the next part, we'll go ahead now and compute r sub y cross r sub theta. Remember, the order doesn't matter, even though the cross product is not commutative. When we take the magnitude of it, it's going to become irrelevant. So we have our I, our J, and our K. So partial of this thing with respect to y would be 0, 1, 0. 0, 1, 0. 0, 1, 0. Then partial of this guy with respect to theta is going to be that negative root 10 sine theta, 0, and root 10 cosine theta. And so from there, we'll go ahead and run that cross product. There's a lot of zeros, so it's not too bad. Negative root 10 cosine theta, 0, and then a negative root 10 sine theta. And now as we go ahead and take the magnitude of this, fortunately with those sines and cosines, the fundamental identity from trig is going to be helpful to us. This thing just simplifies down to the square root of 10. So if I take this thing squared and this thing squared, we'll have a 10 cosine squared, 10 sine squared. The sine squared plus cosine squared goes to 1 when you factor out the 10, and so you're left with the root 10 from the magnitude. So to finish this thing out, we'll have our double integral, we'll have our root 10, and then we'll need some combination of dy and d theta. I'll just go ahead and use dy d theta. They're both constants, so negative 1 to 1, 0 to 2 pi, and that should then give us our setup for the surface area. All right, so for this example, we're going to find the surface area cut from this surface by the xy plane. Or excuse me, not the xy plane, the yz plane. So this is a good opportunity to use that second formula. So x, which would now be a function of y and z, is going to be the 1 minus y squared minus z squared. So that guy right there is a function of y and z, so that's what we're going to be using. And so for this formula, we're going to need f sub y, and then we'll also need f sub z, both of which will be squared, added together, add 1, square root, and then we go. So f sub y would be the negative 2y, and then f sub z would be the negative 2z. So now if I drop those two parts into my formula, I'm going to have my double integral over region R, 1 plus 4y squared plus 4z squared. So I squared that, and then added the 1 with our square root, and then our dA. Now, before I jump into the area, I'm going to take a closer look at what's happening up here when we're cut by the YZ plane. Well, if we're cut by the YZ plane, that's going to imply that x equals 0. So if x equals 0, and I plug a 0 into the surface, then you can see we're going to get a y squared plus z squared equals 1 out of this, which is nothing more than a circle centered at 0, 0 with a radius 1. And I'll go ahead and label this the y-axis and this the z-axis. And so it's pretty clear, even though we don't have x's and y's, we can still use our polar coordinates here. Remember, variables are just random letters assigned. It's how we apply them and in the context we use them that defines what they are. And so for us, what I would prefer to view is the square root of 1 plus 4r squared. And that came from factoring out the 4 there and letting the y squared plus z squared equal r squared. And so this is going to be a very smooth transition into polar coordinates, where my dA would have to be that r dr d theta. And so my r values right here would range from 0 to 1, so 0 to 1 from right there, and then the theta would go from 0 to 2 pi, 0 to 2 pi. So we're still able to make whatever adjustments necessary to get this integral set up and then evaluated as well.